Other questions? Yeah. Okay.
How did you say omega baryon was measured?
Just by looking at the stars and galaxies and estimating from there the amount of baryonic content.
So you measure the you just measure the raw density. I mean, you just go there and measure the density and divide by this critical.
Yeah, exactly. Yeah, yeah. So basically, I mean, you have to you of course cannot go there and measure the density, right? From observation. Yeah, exactly. Right. You estimate how much mass is there in those various stars that you see, right? How much mass is there in the gas, for example, that is in the galaxy, and then based on that you compute this.
And how reliable is it?
I think 0.05 is supposed to be reasonably reliable. Okay? And then there are other constraints which put upper bound on how much omega we can be. But those are more theoretical, right? Which we'll see later, right? But I think people believe that this 0.05 is reasonably accurate. Any other question?
So one question I have. So
yes.
Last time in the end of the class, I think we wrote a grand partition function as product of different types of particles.
Yes.
And you said, I mean, this is because we assume that interaction between different types of particle is not that strong.
That's right. Yeah.
That assumption went to
exactly. Yeah. Because H becomes the sum over the Hamiltonians, right? And then the sum just factorizes.
But at the same time, deciding we are considering the interaction between particles. Like at one time we are considering the interaction, at another time.
Well, you see, in introducing mu, we are not introducing. I mean, that by itself doesn't introduce interactions, right? But of course, you need interactions, right? Even to establish thermal equilibrium, right? Similarly, chemical equilibrium, right? When you are saying that the particle numbers are not conserved, that means there must be some process that makes this transition, right? And this is what you normally do in ideal gas, right? Otherwise, ideal gas will not be in thermal equilibrium ever if you really strictly switch off all the interactions, right? So we are assuming that there is enough interaction to equilibrate, but the interaction energy is sufficiently small so that it doesn't affect the Hamiltonian. Okay, so let me begin by just reviewing what we discussed last time. So essentially, we consider a mixture of ideal gas, of different type of particles. And then we have this relation that 1 over V log Q is 1 over V sum over I. We call this 1 to K. Okay, where K is the number of particles. Particle types. Yeah. Number of particle types. And similarly, we can establish these relations. Rho is sum over I rho I. E is sum over IPI. S is sum over ISI and so on. Okay, because the particles, you just really think of this as non-interacting, so you just add them up, add up the results for rho P S. Then we said that let's assume that there are some conserved charges. Okay, and that I wrote as n tilde L as sum over I CLI Ni, where Ni is the number density of particle type I, and n tilde L is some linear combination of these Ni's. Okay. So the interpretation here is that CLI is the lth charge carried by ith particle. Okay, so if the ith particle carries charge CLI, then if the density of ith particle is Ni, then the total charge density that will contribute is CLI times Ni, and then you sum over all I, because you are trying to calculate the total charge density. Yes.
Lth charge carried by ith particle. So ith particle is some one type of particle.
Say electron, positron, etc.
Lth charge. You mean there are different types of charges of
Say electric charge, right? Baryon number, anything that is conserved. Right? Electric charge, you know, E plus will contribute 1, E minus will contribute -1, but also P will contribute 1, P bar will contribute -1, and so on, right?
So what do you mean by ith particle? Like, for example,
ith particle spaces, right?
so electron, let's say.
Electron, yes. So each electron carries electric charge -1, right? So corresponding CLI will be -1.
Can there be any species which have like L equal to 1 to two different charges?
Yeah, electron, for example, carries both the electric charge and the lepton charge, right? And so it will contribute, the number density of electrons will contribute both to the electric charge and to the lepton charge. Right? Similarly, the number density of protons will contribute both to the electric charge and to the baryon charge. Right? So certainly it can happen that the same particle carries different types of charges. Right? That's why the CLI, right, in general, can be non-zero for different L and different I. Is this clear?
We consider, like, we considering different models in which we will have certain charges that are certain symmetries, whereas in other models there won't be
Yes, it is possible. Yeah. So the point is that any given instant of time, right, what the conserved charges are can change. Okay. For example, take E plus E minus. Okay. You will expect that E plus E minus charge densities themselves are not conserved, right? It's only the difference that is conserved, right? Because E plus E minus can annihilate. Okay. But imagine that you are in a stage of evolution of the universe where the E plus E minus density has fallen off so much that the E minus and E plus doesn't collide. Right? Even if this possibility exists, right? E minus and E plus may not collide. Right? In that case, you will treat the number of E minus and number of E plus as individual conserved charges. Right? So when you talk about conserved charges, it also depends on the period of the type of the evolution that you are talking about. Yeah, and we will see some examples of this later. So the rule again is just like thermal equilibrium, right? We said that particle is in thermal equilibrium if there is enough collision to exchange energy, right, within one Hubble time. Similarly, the particle will be in chemical equilibrium, right, for which these formulae hold, if there is enough interactions for the particle to change its nature, right, go to another particle subject to the conservation laws. Is this point clear? Okay, then we said that if we have conserved charges like this, then in the definition of Q, we insert exponential beta sum over L mu tilde L NL n tilde L. Okay, where these are the chemical potential for conserved charges. In other words, you don't introduce chemical potential for every particle type, right? Which is what we are doing in the grand canonical ensemble to begin with, right? But you introduce a chemical potential for every conserved charge, right? Because proton can get converted to neutron and vice versa, right? Subject to various conservation laws. Okay. And then we said that we can now use this formula, okay, to write this. Okay, this is, I have written this for density, but you can also write this for total number, right, which is the capital N. This I can write as exponential sum over I L and sum over I mu tilde L C L I N I. So this becomes exponential. I can rewrite this just by exchanging the order. Well, mu I okay. So it's as if we have just a sum of collection of ideal gas. Okay. But the only difference is that now all the mu i's are not independent. Right? The mu i's are determined in terms of the mu tilde L's by this relation. Okay. If the number of conserved charges is the same as the number of particles, then of course it doesn't matter. Right? You can take mu i's to be independent. But typically the number of conserved charges is less than the number of particles. Okay, and hence not all the mu i's are independent.
There will be an upper bound, right?
Yeah, total number of independent conserved charges cannot exceed the number of particle species, clearly. Yeah. Right? Because then anything else that you build will be a linear combination of the older charges. So L, so here I have taken L to run from 1 to L. And L has to be less than or equal to K. Yes.
Suppose for some ni's, mu I come out to be 0, and for some ni's, mu I come out to be non-zero.
Yes.
What does that mean for the ni?
Well, we'll see. I mean, we have to convert the mu's to L, right? Because as you saw, that in the whatever formalism you use, grand canonical or canonical, for every particle species, there are two independent variables to begin with, right? You can take them to be mu and t, right? Or n and rho, whatever you want, right? And then the thermodynamics, the various relations, allows you to express everything in terms of the others. So if we have mu I equal to 0, right, it will translate to something on ni, right? Because ni has a formula in terms of mu I. Remember last time we wrote down, I think I did write down this formula. The n is g, so ni is gi over 2 pi square integral dk k square 1 over e to the power beta e minus mu I minus or plus 1. Where minus is for bosons and plus is for fermions, and ei here is square root of k square plus mi square. Right? So if you know mu I, you can calculate what ni is from this formula. I did write down this formula last time, right? Okay, so now what we want to do is to put this in expanding universe. So put this system in FRW universe. In thermal equilibrium, okay, we'll see later how to deal with out of thermal equilibrium cases. FLRW, okay, you can put L anywhere. Okay, so in thermal equilibrium, we assume that Ti is T. All the temperatures are equal. Okay. And in chemical equilibrium, we have this relation. Okay, normally we don't say this because we assume that you have waited for sufficiently long so that the system has come to thermal equilibrium and chemical equilibrium. But in expanding universe, you have to check at every stage, right? So that these assumptions are true or not. So thermal equilibrium means that the particles should be able to exchange energy efficiently within one Hubble time. And chemical equilibrium means that the particle should be able to change its nature consistent with the conservation laws, right? Again, in one Hubble time. No. Chemical equilibrium doesn't mean all the mui's should be the same. Chemical equilibrium means this. Yeah. But that is an equilibrium formula, right? That formula is in even if you have chemical equilibrium, right? You cannot violate conservation laws. If you take a gas with a little more electron than positron, right, and put them together, it will get a mixture of E plus, E minus, and gamma. But the number of E plus and number of E minus cannot become equal because the total charge is conserved, right? Whatever happens. So chemical equilibrium doesn't mean that all the mu's are the same. Right? But it basically means this. Okay? But in an expanding universe, it's not guaranteed that you can use this formula because the expansion rate, right? You have to check, given the expansion rate, whether the particles are allowed to change its nature. Right? This is exactly what I said, that if you have E plus, E minus, right, you would say that the total, what is conserved is the number of E plus minus number of E minus. But if the E plus, E minus is not able to annihilate efficiently within one Hubble time, right, then it's like individually that concept.
Okay. Neither is it true that mu and tildes are the same.
Pardon?
Neither is it true that mu and tildes are the same.
No, mu and tildes are not the same. I mean, you cannot get any better than this. If they're conserved charges, then you have to use this. Right? I mean, the chemical equilibrium that I think you are familiar with is where every particle can change into every other particle. Right? Then, of course, the only conserved charge is the total number of particles, and then the mu will be the same. Right? But these are different kinds of particles we are talking about. Okay, so these distinctions should be made, right? That if you take chemical equilibrium of the type that you are saying that if you have all the mu's are the same, right? If you take two systems, right, say same kind of particles, right, to put them together, then in chemical equilibrium, right, the subsystems have to have the same mu, right? Because then the only conserved charge is the total number of particles, right? Not they're not individual types.
So suppose we're considering a universe in which the particles are such that the reactions that happen, a particle can change into another particle, the reaction. So all the particles can change into each other.
Yes.
In that case, if there is a chemical equilibrium established, in that case, will mu be same?
Yeah, in that case, I mean, most likely what will happen, the mu will be zero. Because if the particles can change into each other, they can also annihilate and become nothing, right? Because the procedure, the process that E plus E minus goes into multiple photons is always allowed, right? So the number of particles is also not constant. Yeah, so the kind of thing that you are talking about is, say, particles which are their own antiparticles, right? Say gas of photon and some other particles which are neutral, right? And suppose there is no conservation law at all, right? They can just transform into each other, right? Produce a number, then all the mu's will be zero. Because if there are no conserved charges, right, then mu tilde L's are zero. And if there are no mu tilde L's, right, then that means that the mu i's are all zero. Is this point clear? Okay, so now let's look at the number of parameters that we have and the number of equations that we have. Right? So the number of parameters, number of variables, not parameters, number of variables is lambda t and mu tilde L. Right? So L plus 2 variables. Equation so far, we have got Friedman equation. Pardon? What is?
What about P and rho? P and rho and
Oh, P and once you give mu tilde L and T,
okay,
P and rho are determined, right? Two variables per species, and then we have reduced the number of variables because in thermal equilibrium there is only one. Okay? So P and rho are not independent variables. That should be clear, right? That
so this you do for both the matter and the radiation.
yeah, for everything, for every kind of species.
But for every species, P and rho can be different.
Yes.
Pi and rho
Pi and rho I, but they are determined in terms of mu I
and T.
and T. And mu i's are determined in terms of mu tilde. Right? So once you give mu tilde and T, you can calculate Pi for every species. Right? Pi and rho I.
Coefficients, CS.
These are given to us. These are just constants because that depends on the particular theory, right? For example, if you have E plus E minus and the electric charge, right? It will get +1 for the positron and -1 for the electron.
Pi and rho were not independent in the beginning, right? I mean,
yes, indeed. They are the equation of state. They are using the fact that the equation of state relates P with rho, right? But what we see now is that this is the situation is a little more general, that you have to introduce two variables per species, right? Not one. There you are assuming implicitly that we only have to give rho I, and then Pi will be determined after rho I, right? But we actually need two.
right. And we actually need to, because you said, I mean, last time that for relativistic, for the extreme cases, it's fine.
Because the number of particles can change, right?
Yeah.
That's why I need two. I mean, the earlier cases that we dealt with, right? The matter, for example, there you assume that the matter particles are just fixed, right? Number of matter particles don't change. Okay. And in the case of radiation, right, we know mu is 0. So that variable was not important. But in general, that is not the case. Okay, so you have the Friedman equation that says the same. And then you have the energy conservation, which is ddt and these you can convert into equations involving mu and t, because rho i's and pi's are determined in terms of mu and mu tilde L and t. We can put?
We can now put K over A naught square equal to 0.
Yeah, we'll do that. I mean, whenever you need to solve anything, we'll do that, right? Right now, I'm just writing the most general case. But I mean, for all actual calculation, I'll just set this to 0.
You said we need two variable means for each particle mu and t.
Mu and t, yes.
In thermal equilibrium, t is
all the t's are the same.
And mu are related by this.
Exactly, right? So that's why we need L plus 2, right? L of the mu tilde, then t and lambda. Okay, and so these equations can be converted into equations involving lambda t and mu tilde L.
in your notation K plus 1 equation.
In K plus 1 equation. No. K can be much larger than L, right?
No. The Friedman and the energy conservation is K plus 1, right? Because the energy conservation equation there.
No.
Oh, no, that's fine.
No, we are not. This is just one equation, right? We are not assuming anymore. Earlier, we got around by saying that each species has conserved energy. That we are not assuming that anymore, right?
Yeah, but if we then assume that none of them interact, and
But none of them interact, but they still interact. I mean, they still interact enough to be in thermal equilibrium. Yeah, if none of them interact, if some particles decide decouple, for example, right? If you find it in one Hubble time, it doesn't collide, then there'll be separate conservation for that.
Yeah, but so we are working for the early universe now.
Yeah, and assuming that there is thermal equilibrium, so none of them interact, right? That assumption is not valid anymore, right? again, we are using the ideal gas formula, right? So we are ignoring the effect of interaction on the partition function, right? But we are assuming thermal equilibrium, which means they can exchange energy, right, via collisions. And at every stage, you have to check which of the assumptions is valid, right? Whether thermal equilibrium is a good description or decoupled evolution is a good description, right? So unlike in thermodynamics, right, or statistical mechanics, where you say that okay, if you wait long enough, it will thermally equilibrate. That assumption you can, I mean, here it's evolving universe, right? So you cannot take that as granted. You have to check at every stage. Okay, this is, I'm assuming that it's in thermal equilibrium, and then these are the equations that we get.
Our universe, if we wait long enough, every species will decouple from each other.
No, because our universe is expanding.
Photon.
Oh, yeah. If you wait long enough, everything will decouple from each other. Exactly, right? Because the densities will be so low. Exactly, that there will be no exchange at all, right? So whatever you set as the initial condition will survive. Yes.
So, the expressions that we got from statistical mechanics, those
Yes.
expressions, are they still valid for non-zero K?
For non-zero K. Yeah, they are valid for non-zero K locally. But the point is, we will not worry about K, because to solving the equations will be much easier if you set K equal to 0. Right? And that early in the history of the universe, these things are the effect of this is very small anyway, right? That as we saw. Because for if you multiply by lambda square, right, this becomes lambda square, this is just a constant. The this side, right, from the radiation has 1 over lambda square. Okay, so that dominates this. In the future, the cosmological constant will dominate. In the past, the radiation will dominate.
So we have to check, for example, this formula that we got from UI, with some UI, that we got from the thermodynamics, right?
Yeah, chemical equilibrium, yes.
Then we didn't ask you anything about the expanding universe or something. So do we have to check whether this particular?
Yes, indeed. We have to check if this thing holds or not. Right? I mean, that is equivalent to saying that we have to check at a given stage, right, what the conservation laws are. Right? If the interactions fall off, right, then new charges can get conserved. As I said, E plus E minus, right, you expect only the number of E plus minus number of E plus number of E minus will be conserved. Number of E plus minus number of E minus will be conserved. But if the interactions are so low, small that they don't collide, then individually any plus and any minus will be conserved. Right? So this formula you can still use, right? But you have to just add new conservation laws.
All these equations are valid for, if we are dealing for early universe means before CMBR, lambda or 10 to the power minus 3, before that.
Yes. After that, everything will be coupled anyway.
Yeah, so all these is for the causally connected points, right? This.
Yes, because you, as I said, I mean, things have to interact so that within one Hubble time they collide. Right? Yeah. So you are not applying this over super horizon scales.
After Big Bang, almost after.
Yeah, this is after Big Bang, but as I said, that not everything is in equilibrium after Big Bang, right? As time evolves, different interactions can fall in and out of equilibrium. So you have to check at every stage, right? That whether this assumption is valid, right? That what you have assumed as conserved charges, whether that's the correct assumption at any given stage. Right? We are also assuming that temperatures are equal, right?
How do we check it?
We'll see. I mean, unless you check it, you cannot do cosmology, right? Because you cannot assume it's in thermal equilibrium unless you are able to check that the processes are strong enough.
So you will check the reaction rate and the expansion.
Exactly. You have to compare the reaction rate with the expansion rate for every process, right?
And for example, neutrinos decouple from the gas early, so
Exactly, right? So you have to determine at what point the neutrinos decouple, and from that point onwards, we have to evolve things differently from what we are doing earlier.
This partition function that you have written will it not be affected if k value is say much larger. I think that's
Yeah, but that never happens, right? If you're thinking of very strongly curved universe, that will never happen in the history of the universe. See, that you are thinking when the curvature becomes of the order of the microscopic scales. That only then thermodynamics or statistical mechanics can get affected, right? But that is never the case, right? Maybe at the time of the Big Bang, right? But we are not going there anyway. So this will be all in the low curvature region.
That might depends on where you.
What?
That might depends on where you do step, like highly curved.
Yeah, if it's very highly curved, right, then you cannot use the flat space intuition anymore, right? Then you have to take into account the curvature of space-time because dynamics itself changes.
how will it affect this partition function highly curved space and partition function?
Well, the energies will change, right? We are using the E equal to square root of k square plus m square, right? That will change, right? And if the density is very large, then even the interaction may not be negligible, right? We are using ideal gas, right? That may not be valid anymore. Yeah, you have to take into account quantum. Okay, the part of the quantum effects we are taking into account anyway because Bose and Fermi gas we are treating differently. Okay, so we need Aylmore equations, right?
What would you mean by highly curved curvature scale with respect to?
The microscopic scale, microscopic interaction scale.
So the radius of curvature should be greater than say Planck.
Yeah, say Higgs mass. When it becomes compared to Higgs mass, then the weak interaction effects, right? You have to see how those could get affected by the curvature.
So basically, the point is that the curvature scale should not go anywhere near the scales that are involved in the theory.
Exactly. Yeah. I mean, it can go near that, right? But then you have to redo your analysis. That's the point. Okay. So, as I was saying that we have L plus two variables, but only two equations, right? So, we need Aylmore equations. And those L equations are going to come from the conservation laws, right? Because we have assumed that some charges are conserved. So, you have to see what their consequences are, right? Because at this stage, I mean, we have not used those. We have not made use of those, right? Except that we are saying that the mu's are given in terms of the mu tilde L's. Okay. So, charge conservation. So this basically says that we have this equation d mu j tilde mu L equal to 0 for L equal to 1 to L, right? This is the usual conservation law for currents. Okay. So this is the conserved current corresponding to the Lth charge, Lth conserved charge. Okay. So in particular, J tilde 0L is NL. Sorry, N tilde L. N tilde L I have introduced anywhere or maybe I have erased. Yeah. So this is N tilde L. Okay. So I'm using the tildes for conserved charges and without tilde are the particle densities, right? Individual particle densities. J tilde L K for K equal to 1 to 3. This you can take to be 0. And that's due to isotropy. In isotropic universe, right, there is no spatial direction in which the vector can point. Right? So on the average, you can just take this to be 0. Okay, so this will then give some condition on N tilde L, and then let's see what condition it gives. Okay, so now if you remember, there is an exercise in GR, okay, that this can be written as 1 over square root of minus determinant G ordinary derivative. Yes.
Due to isotropy is like particles, the motion of particles as I see actual particles, as I see in any direction is same.
Yes.
But these are conserved charges.
Yes. These are conserved currents,
Yeah.
right? But if no direction is spatial, right, then clearly J mu I, suppose you say J mu I is directed in some direction, right? Then that will break isotropy.
J, L, K are linear combinations of J, I,
J1, J2, J3, right? I mean,
K.
yeah. So this is the space direction, right? And what I'm saying is that in a given time slice, right, because there is no particular direction in space which is spatial, right, we cannot have a non-zero value of this. On the average, this will be 0. Right? Of course, individual particles are moving around, right? But we are applying this on the average, right? On the average, this should be 0. Okay, so this is an identity. This is just a GR identity, right? It doesn't say anything about cosmology. Pardon? J tilde, thank you. J tilde mu L. Okay. And once you accept this, then you see that this is equal to 1 over lambda cube. If you remember the free FLRW metric, there is a lambda multiplying the spatial part, right? 1 over lambda cube. And then only the time component is important because the GIs I have taken to be 0 times lambda cube n tilde L. So if this is 0, that means d dt of n tilde L lambda cube equal to 0. Okay, and now we have got L more equations. Okay, so our key ingredient are these L equations together with those two equations, okay, and we will use those to study the evolution of these L plus 2 variables.
There was one over let's take ddt of entropy of L charge L lambda equal to 0.
No, that is not true anymore because the particles can transform into each other. So entropy of individual pieces is not conserved.
What about conserved charges?
Conserved charges by definition, you are allowing particles to transform into each other, right? Charges are still conserved. Conserved charges by definition are the ones that do not change when the particles transmute into each other, right?
So corresponding entropies?
Well, there's a corresponding entropy for each conserved charge. We'll see what relation we can get. Now we have no further equation, right? These are the basic equations. And now whatever else you want to get, you have to derive from this. Right? You cannot introduce any further equation because these are all that we have. Right? You can only derive new equations from this. Okay, and this is what we'll do.
I have a question.
Yes.
That was the charge conservation equation,
Yes.
right? And we are saying, I mean, zeroth component is the charge density.
Yes.
Then we are saying that these vectors should be 0 because of isotropy.
Yes. On the average, right?
Yeah.
At any given point, it's not flowing in any particular direction, right?
So it's more than conservation.
Yeah, this is isotropy. Yeah, this is conservation, right? And here we are just simply using isotropy, right? That we have been using all through anyway. Otherwise, you couldn't have even used the FLRW metric, right?
Okay. So it's the extra input.
Yeah, this is extra. Isotropy has already gone into these equations as well.
But what I was thinking, I mean, that d mu that has the metric, right?
Yes.
So it should follow.
No, it doesn't necessarily follow. J mu is an independent quantity, right? You can have an isotropic metric and you can have a particle moving in that direction, right?
Yeah.
It's only on the average that this should vanish. Individual electrons can move around in space, right? Even
It's a condition on J.
It's a condition on J, exactly.
J to like condition is what? That
J is isotropic, right? Which means only J0 is non-zero and Ji is zero.
Components should be such that, okay, this follows.
Exactly. Right? It's the same that when you wrote down the expression for T mu nu, for example, right? We use isotropy to fix the form of T mu, right? The fact that the off-diagonal terms are zero.
But there, weren't we saying, I mean, the Einstein equations?
Yeah, Einstein's
are
equation,
of that
true. That is true.
require-
But similarly, this J mu will also appear as in the Einstein's equation, right? If you have J mu, if you have particles moving in certain direction, right, on the average, then the T mu nu will get contributions from there, right?
Mhm.
So the whole thing is consistent only if we assume that everything that you introduce is isotropic.
Yeah, develop this derivative that we evaluating the spatial derivative. We can also say that due to homogeneity, that derivative, spatial derivative. So there should not be.
Yeah, you can say that also. Yes, you can say that also, right? But yeah, yeah, it will be zero. I mean, this the point is that the ith term will be zero, right? Only this term survives, and hence we get this, right? And now the point is because n tilde L can be re-expressed in as functions of everything else, right? The independent variables lambda t and mu tilde L. Okay? We can get equations for these. Right? That equation, n tilde L equation, can be converted into equations for these.
I have a doubt.
Yes.
If I have J mu, so that will charge Q.
Yes.
Integrate all the space on J.
Yes, that is true.
So here, the J0, shouldn't it give the CR, those constant, those terms?
No, see J0, you can say, okay, ultimately you can re-express this n tilde L in terms of those ni's. That is true. Right? But we are not integrating over the spatial slice because this is density. N tilde L is local density that you are calculating, right? That's why you have not integrated anything. Right? What you are saying is that indeed n tilde L, right? We had written down that relation. So n tilde L is n tilde L is sum over I CLI NI. Right? So this equation you have to use, right? Because ultimately, if you want to express this n tilde L in terms of those mu's, right? What you will do is that you will use this formula, then you use the relation between Ni and Mu and T, and then you re-express the Mu i's back in terms of mu tilde L.
So this equation has to be interpreted for the average of NLI, right? You can compute the average of NLI.
Yes, so everything is being interpreted for the average, right? Because we have assumed homogeneity and isotropy.
The average of the ensemble.
Yeah, so if you assume thermal equilibrium, right, that means there are enough reactions to so that the ensemble.
I'm just asking to interpret that as L equations for these variables, you would have to then average over the ensemble.
Yeah, true. Yeah. See, if it's true for every case, right, then when you average also it is true. I mean, if we have a gas of electrons and positrons, right, to total charge 0, then any ensemble that it goes to, any state that it goes to, right, it will still have total charge 0. Okay, now let me make a claim. So the claim is that as a consequence of these equations, we have d dt of sum over I 1 to k okay, this is sometimes referred to as the entropy conservation. Okay, so but this is not a new equation, we are going to prove this, right? We cannot take this as a new input. Okay, so let's see how the proof goes. So this is just some algebra. So we start with dSi dt. And SI can be expressed in terms of rho I and Ni, right? Because that's thermodynamics. So you can write this as okay, and now we use the fact that this quantity is 1 over beta. Sorry, this is quantity 1 over t. 1 over t. Is that clear?
Rho and n to be the independent.
Yes, rho and n to be the independent variables.
So, J and J.
So sorry, I didn't get.
You're differentiating a surface of J. I mean, you're summing over the latter, right?
No, in this I have not summed over anything.
SI is a function of rho I and
Yeah, SI is a function of rho I and Ni, right? So no sum over I. I'm going to sum soon. Okay, this is just an individual relation. Yeah, SI doesn't. SI only depends on rho I and Ni, right? Thermal equilibrium. That's a. And then the fact that the Ni's are not independent, that will have to input later. So we get d dt of lambda cube SI as by 3 lambda square lambda dot dSi dt, sorry, SI plus lambda cube d dt of SI and that there I use plus lambda cube over t d rho I dt. Okay, here there is a sum over I. I am just applying this on the ith species. dSi dt is given by the sum of these. Right? Si is a function of rho I and Ni. Right? That's all I have used. Is that clear? Now I'm going to put a sum. Okay. Now we are going to use another relation, which again is a thermodynamic relation valid for individual species, which is that Si is given by rho I plus Pi minus Ni mu I over T. Remember this relation? This was one of the relations we derived in thermodynamics, right? So we are going to use this for every species. This is true. Okay. So using this, I'm going to replace this SI by what appears here. So we get 3 lambda square lambda dot times sum over I rho I plus pi minus ni mu I times 1 over t plus lambda q over t d rho I dt minus lambda cube, sorry, that is sum over I minus lambda cube sum over I mu I over t dni dt. Okay. So first we can get rid of the terms that vanish by the energy conservation. So let's do that. So we look at these terms. Okay. So what do we have? These two together I can write as 1 over t d dt of sum over I rho I times lambda cube. Sorry, I'm going to finish, write the second term also. 3 lambda square lambda dot sum over pi. That by not of freedom, but by the energy conservation is 0. Pardon? By t, yes, thank you. So this is 0 by energy conservation. Is that clear? So then we are left with these two terms, right? The terms that involve mu. So then we get the equation takes the form the d dt of sum over I si lambda cube is given by minus sum over I mu I over t because this term and this term combines into d dt of ni lambda cube, right? 3 lambda square lambda dot times ni and lambda cube times dni dt, and that becomes this, and the mu I over t is multiplied outside. Okay, so in the next stage we are going to substitute for mu I what mu I is in terms of mu tilde L, right? Because we have seen that mu I's are not independent variable. Okay. So I'll write this now as minus sum over I sum over L d dt of ni lambda cube. No, it is not 0 because d dt of n tilde L lambda cube is 0.
Yeah, but then CIL are independent of that. Oh, no, they are not.
Yeah, they are not, they are constants, but this is too many equations. This will be too many equations, right? d dt of ni lambda cube equal to 0 would give k equations.
No, but the linear transformation between Ni and N tilde L is from constant
Yes, but that doesn't, if you have K constant, L constant 0, right? Then those L constants are linear combination of the K other constants.
Okay, you're saying
It's not invertible, right? Yeah, if it is invertible, you could have set this to 0. So this is mu tilde L CLI times ddt of Ni lambda K. But now what we can do is that we can now write this as minus I minus L minus sum over L. We are going to exchange the order of the summation and do the sum over I first. Okay. Then this becomes mu tilde L. Well, I think there is 1 over T which I have missed somewhere. Okay, there is 1 over T, mu tilde L over T, and then ddt of we have used the fact that sum over L CLI Ni is until 9.
by treating C as time.
C are time independent. C's are just charges that each particle species carry, right?
I thought we would, I mean, depending on the time you're at, and hence depending on the temperature, you use like different conservation laws.
Yeah, but that transition will happen out of equilibrium. So this is being applied when assuming the system is in equilibrium, right? During equilibrium. Otherwise, you have to, give up the whole formalism.
But I mean, even then, CIL are just particle properties.
Yeah, they are the particle properties. I think what he is saying is that so CILs will not change, but what charges are conserved will change.
Yeah.
Right? There are more conserved charges added. Why are they not functions of time? See, it's like if you have electric charge, right? The electron carries electric charge plus 1, sorry, minus 1, and positrons carry plus 1, right? Those are the CLIs.
They're constant in time.
They are constant in time, exactly. For all charges, this relation CLI speaks about the microscopic theory, right? In the microscopic theory, you have certain conserved charges, and we assign from the beginning as to what particle carries what conserved charges, right? Like protons carry baryon number 1, neutrons carry baryon number 1, right? The antiparticles carry baryon number -1, and so on. And this is 0 because of this conservation law. Okay, so let me emphasize again that this equation is not a new equation, right? You do not add this as a new independent equation, but the fact that it follows as a consequence of the other equations makes it a useful tool, right? You can use this equation when we need, right? And we'll see that by making a use of this equation, we'll be able to simplify a lot of things. Okay, even though it's not a new equation that you have added to the set that you already had.
But this derivation also probably says that individual DDT is also not 0, right?
No, individual DDTs are all not 0, right? Because if the particles can change their nature, right? If they can exchange energy and so on, right? Then individual particle entropies are not constant.
Precisely because of the CIL in these last steps.
Exactly, yeah. Okay, are there other questions?
These formulas that you are using,
Yes.
they should be used in limited region of universe, right?
Yes, of course. Within horizon. Right? Because thermal equilibrium, you can only communicate over certain distances, right? So you cannot certainly apply it outside that region. So you'll be applying it locally, right? The region should be sufficiently big so that the averages make sense, but it certainly cannot be as big so that thermal equilibrium doesn't get established.
What is the statement saying? Intuitively that the total entropy is constant.
Yes, total entropy per unit volume. Yeah, total entropy is constant, exactly. Total entropy per co-moving volume is constant. Exactly. Right? And this is what the kind of thing you would expect, because in equilibrium statistical mechanics, you know that the entropy is conserved. Right? And here, even though things are evolving in time, we have assumed that the evolving is slow enough, the evolution is slow enough, so that at every stage you can use equilibrium statistical mechanics formula. That's effectively the expansion of the universe you are thinking of regarding as a quasi-static expansion.
Will increase when it's non-equilibrium state.
Yeah, once it goes out of equilibrium, the entropy will increase.
Completing that in the bracket of the left-hand side, is that the entropy of the universe?
This is the entropy per unit co-moving volume of the universe.
The audio and video appear to have been turned off. The audio and video have been turned off. Could this be corrected, please?
So for any conserved charge, right, microscopic charge, the particle and antiparticle carries opposite charge, right? And this means that CLI is always equal to minus CLI bar, where this I and I bar, therefore, so I refers to particle, this refers to antiparticle.
But for some like photons,
So for photons, CLIs are all 0. So 0 is always equal to minus 0, but yeah. So the particles which are their own antiparticles don't carry any charge. Okay, this is a general feature, and we are not going to make use of this general feature. Okay. So this basically means this, right? CLI equal to minus CL bar I. This is assuming that this annihilation process is in equilibrium. Right? If the annihilation process is not in equilibrium, then of course you can define separately electron charge and electron number and positron number, right? And they will be separately conserved. But those cases, I mean, in fact, we can do it much easier, right? You don't have to go through all this formalism. Okay? So we'll use this, and this means that if you look at the formula for mu tilde mu I, right, which is sum over L CLI mu tilde L. Okay? So this equation means that mu I equal to minus mu I bar. So particle and antiparticle will carry opposite chemical potential in any situation. Is it clear?
Can opposite charge, you mean, can the opposite charge that are conserved, right, in this?
Yeah, so if you take any conserved charge, right, you'll have to assign the CLIs, right? And particles and antiparticles always carry opposite value of CLI, right? Like E plus carries a positive charge, E minus carries negative charge, right? Lepton number, E minus carries positive lepton number, E plus carries negative lepton number, and so on.
For all conserved charges, this is.
For all conserved charges in a microscopic theory, this is true.
how do you define non-equilibrium process? Like this is equilibrium.
Yeah, so we'll see what to do when things go out of equilibrium.
So how
Right.
do you define out of equilibrium?
When the number of collisions is less than 1 per Hubble time. Right? So basically that is the guiding principle, that the number of collisions per Hubble time should be large enough. Right? And large enough, we normally take 1, because typically the rate falls off reasonably fast. Right? So 1 is a good number. Right? Which means that a little earlier the rate would have been much higher, a little later the rate would be low. So if we now look at the formula, Ni was Gi over 2 pi square integral k square dk. So then the corresponding Ni bar will be given by Gi over 2 pi square integral k square dk 1 over e to the power beta Gi of k minus plus mu I plus mu I plus 1. The degeneracy factor is the same. So let's look at the relativistic limit first. mu I bar, I have written it as minus mu I. It would have been minus mu I bar, right? I wrote it as mu I.
What about here?
What about?
Yeah.
EI is the same, right? EI will be, sorry, EI of K is square root of K square plus mi square, and particles and antiparticles have the same mass. Okay, so EI is the same both cases. So relativistic limit is when K is larger than mi, much larger than mi. In that case, Ni is given by Gi over 2 pi square. Let me write the formula for Ni and Ni bar both. Or maybe I write it separately, I will get confused. Ni is and now let me also write down the expression for n gamma, which is 2 over 2 pi square, because G is 2 for gamma. Gamma is its own antiparticle, yes, indeed.
So this n gamma that you have written with Gi equal to 2.
Yes.
So this is for like particle part of photon, and then two other two.
No. There is, because photon is and its antiparticle are the same, right? So photon has two polarizations, and I have written that's the two.
So that's for photons, right?
That's a photon. N gamma. Gamma is the photon. I'm using exactly the same formula with
For gamma, for photon, all CLIs are 0.
yeah, all CLIs are 0. So mu is 0 for photon, right? That's why I've not written any mu. Neutrinos, okay, depends on how you count it. Antiparticle of neutrino is not the same, right? So neutrinos you count as having one helicity state. So G will be 1, and antiparticles will be different from particles in general. Pardon?
I didn't understand that.
He was asking about neutrinos. Neutrinos are not their own antiparticles, right? So you count particle and antiparticle separately, and their mu's will be different in general. Now the point is the following, okay, that suppose, so this is a simplified situation, but this can be generalized, okay, but I think it will illustrate the point. Suppose Ni minus Ni bar is conserved, and we know that Ni minus Ni bar over n gamma is small.
This is a average. Okay, everything is average.
Yeah, everything is averaged anyway. Right? So let's imagine that we know for some reason that Ni minus Ni bar over n gamma is small. Right? Like for baryon, for example, it's 10 to the minus 9, as we saw, right? And typically all the asymmetries that we know in the present universe has this property that the asymmetry is small. Right? It's small in the sense that not in terms of mass, but in terms of the number of particles. Then from this we can see, right? You see for large temperature, these are these quantities, right? If n gamma if ni minus ni bar is small compared to n gamma, right? That basically means that mu must be small, or more specifically, beta mu must be small. Is that clear? Because there's one is plus, minus one is plus. So if beta mu was of order 1, then these will differ, and the average n gamma will be somewhere in between.
But this is an analysis at large K.
Large, I mean, you have taken this to be relativistic. So beta, so if the temperature is high, right, then the only part of the integral that contributes, right, gives the major contribution is large K.
Okay.
Okay. So this will imply that beta mu is small. Beta mu y, yes. Okay. And in fact, for most of our analysis, right, for whenever we'll basically not take into account this isometry, right, except when the this asymmetry is important, right. Otherwise, we will say that okay, you can just set beta mu y equal to 0. Okay, the fact that there is a small amount of excess proton over excess baryon over antibaryon, right, or lepton over anti-lepton. Okay, charge of course is identically 0 anyway. That those effects will simply not take into account for the global evolution of the early universe, right? We have to take those effects into account when we actually focus on those effects, right? But not in the global evolution. Okay, so we'll set beta mu I equal to 0. Because okay, you see, if you are saying that ni minus ni bar is comparable to n gamma, right? That will require that beta mu I is of order 1, because these is the only difference, right? Okay. On the other hand, if this is small compared to n gamma, right, then beta mu I must be small, because if beta mu I is not small, right, then these will differ. Right, and when you calculate the ratio, you will find this of order 1. Right, it's just the fact that if beta mu I is 0, then these two are exactly equal. Right? And for most purpose, right, we can just ignore the asymmetry.
And you said something about the asymmetry. Like, how do we know physically ni minus ni bar is small compared?
Well, today we know what NB is.
Right.
And we know what n gamma is, because we know the micro background temperature. Right. So NB over n gamma we calculated is like 10 to the minus 9 or something, right? So, and in the early universe, of course, you can say, well, this ratio might have been different, right? And indeed it was somewhat different, but not order of magnitude different, right? We'll see how different it was. And that's something that we can calculate. Right? So NB, so the point is NB over n gamma, right, was small in the early universe. Similarly, NE over n gamma, right, NL over n gamma, where L is a lepton number, was also small in the early universe, right? As far in the current universe and hence in the early universe. So we'll take these asymmetries to be small.
Early universe was radiation dominated, so NB by n gamma would have been certain now also.
Well, the point is baryon could have been relativistic, right? In the early universe, the temperatures are higher, so baryons could have been relativistic, right? So the actual baryon and antibaryon numbers would have been comparable to n gamma. But the difference, right, because of the baryon number conservation, you cannot get rid of the difference, right? And so the point that difference is small compared to the actual value, right? Indeed. So NB, when the baryons are relativistic, right, NB and NB would have been of the same order as n gamma. Because as you can see, the mass drops out in this formula, right? In the ultra-relativistic case.
And you said something about the asymmetry. So, like, how do we know physically ni minus ni bar is small compared to ni gamma? Well, today we know what n B is, and we know what n gamma is. Because
Well, Yes.
So when you're saying is small, we are considering the time before CMBR.
Yes, yes. Everything is happening before CMBR. Yeah. Okay, now there is one point which we have to remember.
Before we said this beta mu is to beta is anyway it is very small in the early universe. We have to really do something. How much difference is there with the beta k and beta?
Okay, we'll consider a situation where beta mu I cannot be set small, even though this difference is small. Right, we'll come back to that. But let me just say one thing, that we said that all the observed asymmetries are small, right, compared to n gamma. That is indeed true. Okay. But we do not know if the neutrino asymmetry is small, because the neutrinos are so weakly interacting that nobody has detected any neutrino in the cosmic background. Right, even though we'll see that those should be there. Okay. So we don't know if the neutrino asymmetry is small, right? Maybe they are only neutrinos and not antineutrinos, right? And they are of the same order as n gamma. Right? So this will be an assumption. We'll assume that asymmetry is small even in the neutrino sector. Okay, so that for our most purpose in the relativistic situation, we can take the mu's to be 0. See, if you take the mu tilde to be 0, then all the mu i's will be 0, right? The formula simplifies, right? So that's, otherwise you can do the analysis even with the non-zero mu's, right? Is that the formula looks more complicated. So we'll say, we'll proceed by setting mu is equal to 0. Okay? But this assumes that the neutrino asymmetry is also small. Okay, later on we'll try to justify it. Okay, but for now it will be an assumption. Is this clear? Okay, now let me explain a situation where this assumption, this assertion fails, that beta mu can be taken small. Okay. So for this, let's consider the non-relativistic case. Where T is small compared to Mi. Okay, if T is small compared to Mi, then the kinetic energies will be small compared to the mass energy. Okay, so that's the non-relativistic case. In which case we can approximate Ei by Mi plus Ki square by 2m. Okay. So let's see what we get for here. So Ni will be given by integral energy I over 2 pi square Is this clear? So beta Mi is large, right? Because T by definition is small compared to Mi, right? So T is 1 over beta. So beta Mi is large. Let's suppose that beta mu I is small. Okay, as we assumed earlier. I mean, also a contradiction in assuming that beta mu I is small. But let's suppose that beta mu I is small. So then this can be approximated if beta mu I is small. Then this can be written as Gi over 2 pi square integral k square dk 1 over beta, sorry. Okay, because if this is small, then since e to the beta mi is large, right? This is also larger than 1, clearly. So you can ignore this minus plus 1. Right? It basically becomes the standard Boltzmann statistics. Okay. So this is a Gaussian integral. Okay. So this gives you e to the minus beta mi. Okay. And you can actually do this integral. In fact, you can do this as a Gaussian integral, you can do it exactly. Okay. But roughly it becomes, I think, m over beta I, yeah, this should already be mi. Is this clear? Right? I mean, this factor you can get simply by scaling k, right? By square root of mi by beta. Right? The actual integral also you can do. This is Gaussian integral, but this dependence you can get just by scaling k. And similarly, ni bar will be also the same because you have said beta mu equal to 0. Beta mu I is assume that small compact to 1. Right? And we are going to show a contradiction in that assumption. So this difference is 0 as written, right? But that of course was expected because you assume that ni minus ni bar is small anyway. But the problem you see is that we assume that okay, there is some error. So once you take into account that error, this difference will become what we want. You have to take beta mu I not 0 but some small number. But you see that according to this formula, right? These are the dominant formula for ni and ni bar. This one falls off rapidly when beta mi becomes large. So at some point, what will happen? Okay, so let me then write ni minus ni bar over n gamma. Okay, maybe I should have said that also. So this you can check again by scaling that this goes as 1 over beta q. Okay, the scale k, beta k equal to u, right? It will go as 1 over beta q. So you multiply by beta. So this goes as e to the minus beta mi times beta mi to the power 3 by 2. So suppose, sorry, I made a mistake. Ni over n gamma. Ni over n gamma. And similarly, ni bar over n gamma is also e to the minus beta mi. And you assume that there are small corrections to this formula which gives the correct ni minus ni bar. But at some point, what will happen as temperature is reduced, right? Beta mi is increasing. So at some point, it may happen that beta mi is so big that individually these numbers become smaller than the expected ni minus ni bar over n gamma. Right? So if e to the minus beta mi times beta mi to the 3/2 becomes less than or order ni minus ni bar over n gamma. This is the observed. This is based on observation. Then clearly there is an inconsistency. Right? You are saying that individually these are both small compared to ni minus ni bar over n gamma. So how can the difference be of order ni minus ni bar over n gamma? Right? Yes. So what you are saying is that ni over n gamma has this plus some small correction, and ni bar over n gamma is this plus some small correction. Right? That small correction is supposed to reproduce this ni minus ni bar over n gamma. right? But if these expressions themselves fall below what we want for ni minus ni bar over n gamma, right? Then the fact that the corrections are small is not tenable anymore, right? Because suppose it's these plus small corrections, right? Then ni minus ni bar over n gamma will be less than this, right? But we know what this is, what you want, right? For baryons, for example, you need something like 10 to the minus 9. Right? For sufficiently low temperature, this quantity can be much larger, less than 10 to the minus 9. So at some temperature, what is going to happen is that it's no longer tenable to say that beta mu is small. Because if we assume that beta mu is small, right, then individually ni and ni bar, okay, will go below the expected result for ni minus ni bar over n.
You're saying that term is very less.
Yes.
And we have these expressions.
Yes.
And in some case, if like these individual expressions, these go below this another expression, ni minus ni bar.
Yeah. So for this, it's not an expression. It's something that you want. Observe. Exactly.
The observed value of
Exactly.
then what the correction is.
Yeah. So if that happens, then this formula must be wrong.
Okay.
Right? And these formula are derived assuming that beta mu is small. Right? So it must happen that beta mu is no longer small. Right? So what has to happen in this case, right? I mean, let's see why the manipulations that we did here, right? We assume that this term is large enough so that we can ignore this, right, and proceed with this. Okay? But that assumption must fail. Okay? This means that this quantity mu I must approach mi so that it doesn't become too big, because a too big a denominator will make too small a numerator, right? So you have to somehow keep this small, and that can happen by mu approaching m. Okay? But if mu approach m, then you can see that this may remain finite, but the other one where this is plus will go to 0. You cannot keep both particle and antiparticle densities small, right? One of them, sorry, both particle and antiparticle densities finite. One of them have to go to 0, okay? But one of them you can keep finite. So what has to happen, right? Suppose the temperature comes down, right? And you know there is a small excess of particle over antiparticle. Okay? Once the temperature comes down, right, what will happen is that the mu will have to adjust itself. So mu is something that is supposed to be determined in terms of the various inputs, right? The initial condition. So mu has to adjust itself, okay, so that if there is an excess particle, right, then mu has to adjust itself so that the particle density remains to whatever you want, okay, but the antiparticle density will be very small. Okay. So we'll try to illustrate this next time, right, using the baryons, right? I think it will become clear, right? Imagine that you have baryons and we are looking at 10 MeV, right? You know that there is an excess density of protons over antiprotons, for example, right? At 10 MeV, right, proton mass is 100 GeV, sorry, yeah, 1000 MeV, right? 1 GeV is 1000 MeV. Okay. So beta m, so if beta is 10 MeV inverse and m is 1 GeV, then beta m is like 100. Okay. So this formula, if you use, right, it will tell us that proton and antiproton densities are going to be of the order e to the minus 100, right? Which cannot be true because we know that NB over n gamma is 10 to the minus 9. Right? E to the minus 100 is much smaller than 10 to the minus 9. Okay. So at 10 MeV, if you are looking at what is the mu for the protons, right, we know for sure that the mu cannot be close to 0. Right? Beta mu cannot be close to 0. In fact, what will have to happen is that mu has to come close to the proton mass, so that this term remains large but finite, right? Not smaller than 10 to the minus 9. Okay. And as a result, the other term, the antiproton density, right, will be very small.
Can you adjust itself?
mu is given by the initial condition, right? So mu is a dynamical variable, right? If you put it on a computer and solve it, it will happen automatically, right? NB over N gamma is an input. You know that is the condition, and then you evolve it in the computer. It will automatically happen that mu will evolve into something close to M, right? I'm just giving an argument as to how this will happen, right? Because the equations have to be satisfied, right? So the only way the equations can be satisfied if mu evolves in such a way, right, that as the temperature is coming down, right, mu has to go close to the particle mass, right? So that this one of these, right, depending on whether there is excess particle or excess antiparticle, right, one of these will have to remain finite, while the other one will become infinite.
Particle and antiparticle that will also know from this variant.
Exactly. Whether there is excess particle, suppose there is excess particle, right? Then we know that this we cannot make very small, right? So you have to take this mu I to be close to mi, right? If there is excess antiparticle, then you have to take the mu I to be close to minus mi, right? So that this other term becomes large.
The electricity equations that you obtain,
Yes.
they will govern that given the initial conditions, they will tell us how lambda, T, and mu and tilde evolve.
Evolve, exactly.
From that you can find out mu i's. And you are saying that as the temperature comes on through the dynamics only, we can take non-relativistic limit, but at the same time mu I will flow to m.
Exactly. That's right. Right. If you actually put it on a computer, and if you say I don't want any analytic understanding, I just evolve it, right? Mu I will automatically evolve towards mi, right? Because the computer will make sure that the equations are satisfied, right? But this is a physical understanding of what will happen in that limit, right? Because for most of the analysis, we will try to get as much as possible without using numerical simulation, right? But just from based on physical understanding of what the situation will be, and that's what will happen. That for non-relativistic cases, right? Once that it goes sufficiently non-relativistic, then the only way you can maintain an asymmetry is to make mu close to m or minus m.
It's completely okay to assume it's the universe because it's very large temperature. So they already.
Yeah, when the temperature is above the proton mass, they didn't have to worry, right? But we'll be considering situations where the temperature was say 10 MeV. Okay, there you cannot take the mu for the baryon to be 0 anymore.
At 10 MeV, thermal equilibrium.
Yeah, thermal equilibrium will still be there. Tomorrow, yeah, we can meet after the class maybe, after lunch. Okay.